Hi students, welcome to another wonderful session. Today we are going to deal on the chapter metals and nonmetals. We are familiar with infinite number of metals and nonmetals in our daily life. As you can see here, there are different types of nonmetals and metals that occur in the nature. Few of them are brass, copper, steel, which comprises the metals. Among nonmetals, they are silicon, sulfur, iodine, graphite, etc. So, how do metals and nonmetals differ? As we have studied in the previous classes, in the minor classes, certain physical properties determine the main difference between a metal and a nonmetal. So, as you can see here, while examining the physical properties, a major difference can be observed. Metals in their pure state have a shining surface. This property is called metallic luster. On the other hand, nonmetals lack this. As you can see, this is aluminium. When we rub aluminium surface with a sandpaper, it shines. This shows the lustrous character. Similarly, when we do the same for a nonmetal like sulfur, it won't happen, which means nonmetals are not lustrous. Next, metals are hard, hence they are used in making machinery, buildings, etc. Nonmetals are brittle. For example, let's consider a pencil. A pencil is made of graphite, which means we can break that simply. That is brittle. In the case of iron, iron is a strong metal which is hard. So metals are hard. As you can see here, this is a plate of gold which is beaten up into thin sheets. Metals can be beaten into thin sheets. This property is called malleability. Metals are malleable, but non-metals are non-malleable. Similarly, metals can be drawn into thin wires. This ability is called ductility. As you can see in the picture, copper metal is used in our homes as electrical wirings. Copper metal can be easily drawn into thin wires. This ability is ductility of copper. Non-metals are not ductile. Metals are conductors of heat and electricity. Just view the image here. We are connecting an apparatus as shown. We are connecting a sample whose one end is connected to a end of battery, whose another end is connected to a bulb. The end of the bulb is connected again to a battery. If you switch on the battery, if the sample inserted between that two columns is a metal, the battery glows. If it is a non-metal, the battery never glows, which means metals conduct electricity. Non-metals does not conduct electricity. You can see here, copper wire is used in electrical wiring. Similarly, in the case of conducting heat, the cooking utensils that we use at our home is made of metals like stainless steel and other things, etc. So these are good conductors of electricity and heat. Metals have high melting points. Just view this apparatus here. We are connected a thin metal wire which is undergone to have burning by keeping a burning mantle below that. To the thin wire, we have applied wax and we have adjusted a pin in the wax. As the heating occurs, as the heating proceeds, the wax melts and the pin drops down. What has happened here? This is an activity given in your textbook. The thing happening here is, the heat is conducted over the metallic wire and the heat is conducted through the wax. The heat melts the wax and the pin drops down. So that's what happens in this activity, which means metals are good conductors of heat. Similarly, here you can see, even after applying this much heat, the metallic wire didn't melt. This means metals have high melting point. Next, this is a piece of insulation copper wire you can see at your home when you look at the electrical wiring. The copper wire is covered with PVC insulations or rubber-like insulations. This is to prevent electrical shocks. Since plastic, PVC, rubbers are non-metals, they are plastics, They does not conduct electricity. Metals hit by a hard substance make sound. This property is called sonority, which means metals are sonorous. This is why the cymbals make sound, the bells make sound. So in this case, when metals are hit by a hard substance, it definitely make a definite sound. That's why metallic bells are kept at schools for bell breaks. So, summarizing all this, if we just examine the physical properties alone and try to differentiate between a metal and a non-metal, we can see metal is lustrous, non-metal is non-lustrous. Metal is hard, non-metal is brittle. Metal is malleable, non-metal is non-malleable. Metal is ductile, non-metal is not ductile. Metal is a good conductor of heat and electricity, non-metal is an insulator. Metals have high density, non-metals have comparatively lower density. Metals are sonorous, non-metals are non-sonorous. Metal typically exists as solids, non-metal exists as solid, liquid or gas. Till here we saw the difference between metals and non-metals based on their physical properties. But there are several exceptions, which means the main difference between a metal and a non-metal cannot be confined to the difference based on the physical properties. The exceptions are, as you can see, all metals except mercury exist as solids at room temperature. Mercury is a liquid at room temperature. You may have seen a thermometer. In the bottom portion of thermometer, mercury exists. If we just break the thermometer, we can see liquid mercury flowing down, which you can see in the picture. Next, gallium and cesium have very low melting points. We just saw metals have very high melting points. Gallium and cesium has very low melting points, which will melt even if you kept it on your palm, which you can see here. This is gallium. Next, iodine is a non-metal, but iodine is lustrous. We just studied metals are lustrous, non-metals are non-lustrous, but iodine is a non-metal, it is lustrous. Similarly, for carbon is a non-metal existing in different forms. One of its main form is diamond, which is the natural hardest substance, having high melting and high boiling points. Remember, carbon is a non-metal. Graphite, another form, is a conductor of electricity. Remember again, carbon is a non-metal. Non-metals does not conduct electricity. This is what we just studied. But graphite conducts electricity. Alkali metals like sodium, lithium, potassium are too soft that they can be cut with a knife. We studied metals are hard. This is another exception. They have low densities and low melting points. So, what does these exceptions mean? This means that the main difference between a metal and a non-metal cannot be explained only with the typical aspects of physical properties. So, certain properties which means chemical properties also must be included to explain the difference between a metal and a non-metal. So, next we can go for chemical properties. So, coming to chemical properties, first we are dealing with the reaction of metals with oxygen. Metals combine with oxygen to form metal oxides. Metal plus oxygen giving metal oxide. We can much more clearly understand this with the help of examples. When copper is heated in air, copper oxide forms 2Cu plus O2 giving 2CuO. Copper oxide reacts with hydrochloric acid. CuO plus HCl gives CuCl2 plus H2O. Copper chloride is formed here. This is an example that we learned in the previous chapter. A salt is formed here plus water, which means copper oxide is a base. Next example, aluminium forms aluminium oxide. Al plus O2 giving Al2O3, aluminium oxide. Also, aluminium oxide reacts with HCl as well as NaOH, which means it reacts with an acid and it reacts with a base. Al2O3 plus HCl gives AlCl3, aluminium chloride. Al2O3 plus NaOH gives NaAlO2 sodium aluminate. Such oxides showing both acidic as well as basic behavior are called amphoteric oxides. Most metal oxides are insoluble in water. Oxides of alkali metals are soluble in water. Sodium oxide Na2O plus water gives sodium hydroxide. Potassium oxide K2O plus water gives potassium hydroxide. This is the typical property of alkali metals. The oxides of alkali metals which is treated in water, which is soluble, gives their respective hydroxides that are also soluble in water. Different metals shows different reactivity towards oxygen. For example, if we just keep metals like sodium, potassium or lithium in open air, it immediately catches fire. As you can see in the picture, this is potassium immediately catching fire when it's kept open. Hence, they are kept immersed in oils. Also, you might have seen oils like kerosene oil are also used. As you can see in the picture, lithium, sodium and potassium are kept immersed in oils to prevent their fire catching capability. Next, reaction with water. Metals react with water and metal oxides are formed, plus hydrogen gas. Most metal oxides, as we just discussed, are insoluble in water. Those are soluble in water which dissolves further and they again forms a metal hydroxide, which means metal plus water gives metal oxide plus hydrogen gas. That metal oxide which is soluble in water again reacts with water, dissolves in the water and gives metal oxide plus water giving metal hydroxide. Metals like sodium and potassium reacts very violently with cold water. The reaction is very exothermic and the evolved hydrogen immediately catches fire. The picture you are seeing here is that of sodium catching fire when it is put in cold water. The reaction is highly exothermic. Na plus H2O giving NaOH plus H2 plus heat energy. A very big amount of heat energy is liberated. Calcium doesn't react violently with cold water. It starts flowing because of the bubbles are stitched to the surface of the metal. The hydrogen gas are formed, the bubbles get sticked to the surface of calcium. As you can see in the picture, this is calcium floating on water. Ca plus H2O giving CaOH twice calcium hydroxide plus hydrogen gas, which is H2. But magnesium doesn't react with cold water, but react with hot water to form magnesium hydroxide and hydrogen gas. Such same as calcium, magnesium floats on water. Mg plus H2O giving MgOH twice magnesium hydroxide. Metals like aluminium and iron do not react with cold or hot water, but they react with steam, which is the gaseous state of water, which is Al plus H2O G, which means it is steam in the gaseous state, giving Al2O3 plus H2 aluminium oxide. But metals like lead, copper, silver, gold, they don't react with water at all. They are least reactive with water. Next, reaction with acid. The general reaction may be metal plus acid giving salt and hydrogen gas. But there is a small difference when this happens with nitric acid. If the acid is nitric acid, hydrogen gas is not evolved. This is because nitric acid is a strong oxidizing agent. If hydrogen gas is liberated, nitric acid oxidizes that hydrogen to water, which means H2 is oxidized to H2O. And the nitric acid itself gets reduced to nitrogen oxides. But there is a small exception. Manganese and magnesium, they react with very dilute HNO3 to evolve hydrogen gas. Next, reaction with solution of another metal salt. This is a particular reaction that we have studied in the previous chapter. More reactive metal displaces less reactive metal from its salt solution. For example, if A and B are two metals, if A is more reactive than B, then metal A plus salt solution of metal B gives salt solution of A plus metal B, which means A displaced B. A is reactive than B. Let's look it with an example. Just imagine there are two test tubes here. On one test tube, you have dipped an iron nail in a copper sulfate solution. In another test tube, you have dipped copper wire in iron sulfate solution. If you just wait to see the change that happens here, you can see iron displaces copper from copper sulfate. Iron is more reactive than copper, so this happens. Copper is less reactive and it will not displace iron from iron sulfate. The reaction happening here is Fe plus CuSO4 giving FeSO4 ferrous sulfate plus copper. This is a particular reaction that we studied in the previous chapter. So as the time goes, in the first test tube, the displacement reaction occurs. Next, the reactivity series. As the name suggests, it is a series having different reactivity of elements. Different metals have different reactivity, right? The reactivity series is an arrangement of metals in the decreasing order of their reactivity. As you can see here, this is a reactivity series of metals. Potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, copper, mercury, silver, gold. Between lead and copper, hydrogen is placed, which means the elements which are coming under hydrogen are less reactive than hydrogen, which is coming above hydrogen are more reactive than hydrogen. The elements in the top is the most reactive, elements in the bottom is the least reactive. So this is the reactivity series of metals. Next, reaction between metals and non-metals, the formation of ionic compounds. What is a reactivity at a basic definition? The basic definition is the reactivity of an element is simply its tendency to attain a stable octet configuration in its valence shell while they are forming a compound. Elements typically do this while they are forming a compound. The ease with which they do is the reactivity. This can be easily explained with some examples. Example 1. Let's take with sodium. Sodium has three shells in its main state, K, L and M. In the M shell, it has one electron. So, to have a complete octet configuration in the valence shell, there are two ways. Either sodium can gain 7 more electrons and have an octet configuration for shell M. Or sodium can lose one electron and can have the loss of the M shell and it can have the octet configuration for the L shell. Since sodium is a metal, it is easy to lose an electron. Sodium loses one electron and as you can see here, the L shell is the valence shell, it has 8 electrons. So by losing one electron, sodium has attained an octet configuration in its valence shell. Now Na has changed to Na plus since it has lost one electron. Similarly, chlorine, it is a non-metal. It has 7 electrons in its valence shell, which is M shell. It should gain one more electron to have octet valence shell. So as you can see here, if chlorine gains one more electron, it can have an octet configuration in its valence shell, and since the electron is gained, Cl changes to Cl minus. So as we just saw, Na changes to Na plus in the previous case, Cl changes to Cl minus in this case. So just imagine, if sodium and chlorine reacts, the electron lost by sodium can be taken by chlorine. As you can see here, both images show the valence shell of sodium and chlorine. The electron, the one electron in sodium is taken by the chlorine and now Na plus and Cl minus are here. In such a case, in this case, NaCl is formed, sodium chloride. Na plus and Cl minus have an electrostatic attraction between them. This holds together the sodium chloride compound. But there is a peculiarity. It does not exist as molecules, which means the sodium chloride compound does not exist as NaCl, 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 etc. But it exists as aggregates of oppositely charged ions, which means Na plus, Cl minus, Na plus, Cl minus, and so on. So in such a way, an ionic compound is formed. This is what an ionic compound is. Let's look at another example. Let's look at with magnesium. Magnesium has the N shell as its valence shell. It has 2 electrons. To attain an octet configuration, it loses 2 electrons and the L shell becomes its octet valence shell. Now Mg has changed to Mg2+. So if magnesium and chlorine were to react, if chlorine is reacting with magnesium, it can only accept 1 electron. Right, one chlorine atom can only accept 1 electron. But magnesium lost 2 electrons. So 2 chlorine atom comes into reaction with 1 magnesium, and as you can see here, such a kind of reaction takes place, giving Mg2+ and 2Cl minus. And magnesium chloride MgCl2 is formed. This is how MgCl2 is formed. So 2 Cl atoms come into action. So briefing, compounds formed by this kind of electron transfer are called ionic compounds. They have certain properties. First, physical nature. They are solids and somewhat hard due to strong electrostatic force of attraction, but they are generally brittle and break into pieces when pressure is applied. Melting and boiling point. They do have high melting and boiling points, since they have very strong electrostatic force of attraction between oppositely charged ions. Solubility. They are generally soluble in water but insoluble in oils like kerosene, petrol, etc. Conduction. They conduct electricity in the molten state. It is because in the pure state they exist as oppositely charged ions arranged together as solids. In such a case, ions cannot move. When ions move, electricity is conducted. Coming to molten state, ions are able to move, and in the molten state, ionic compounds can conduct electricity due to the movement of oppositely charged ions. Next, the important part in this chapter, the extraction of metals. The elements occurring naturally on Earth's crust are called minerals. This you have studied in your previous classes. The minerals containing a high percentage of particular metal and has a chance of extracting it are called ores. So metals are extracted from their ores. So different elements have different reactivity and their presence in the nature differs. As you can see in the reactivity series, different metals have different reactivity and there are different methods to extract the different reactivity metals. As you can see here, the first section, potassium, sodium, copper, magnesium and aluminium are mainly extracted by electrolysis methods. Zinc, iron, lead and copper are mainly done by reduction using carbon. And silver and gold, these are least reactive, so they are mostly seen in free state in nature. So they are easy to extract. In the next picture, you can see the main steps involved in the extraction of metal from their ores. The ore is mainly classified into 3 different segments. The metals of high reactivity, the ores with metals of middle reactivity, which means medium reactivity, the metals with ores of low reactivity. For the high reactivity, as we just discussed, electrolysis of molten ore is treated, which is then converted to pure metal. For the metals of middle reactivity, there are carbonate ores, there are sulfide ores. Carbonate ores are done extraction by calcination process, sulfide ores are done extraction by roasting process. These 2 processes gives the outside of the metal, which is then reduced to the metal, which is subjected for refining to obtain the pure state. Next, metals of low reactivity. Mainly sulfide ores are present here. This is done for roasting. This is then converted to the metal state, which is done for refining. So these are the small briefing of the different reactivity metals that is getting extracted by different methods. Concentration of ores. As the name suggests, the concentration is simply the treatment of ores to make it really pure. Ores mined from the earth are usually contaminated. These impurities are called gangue. The process are based on differences between the physical or chemical properties of the gangue and the ore. There are different kinds and various separation techniques. As you can see in the picture, there are two broad techniques: froth flotation process and magnetic separation. These are the two main concentration processes that we do for ores while extracting the metal. Extraction of metals. So, as we just discussed, there are different extracting methods for metals in the low activity series, for metals in the medium of the activity series, for metals in the high in the activity series, which means for reactive activity metals. First, we can discuss extracting metals low in the activity series. They are very unreactive. The oxides of these metals can be reduced by just heating. For example, cinnabar, mercury sulfide, HGS. It is an ore of mercury. When heated in air, HgO, mercuric oxide, is formed, which is reduced to mercury on further heating. HGS plus O2 giving HgO plus SO2. HgO is simply heated when we get mercury plus oxygen gas. Another example is copper, which is found in copper sulfide ore. It is also obtained by heating in the air. Copper sulfide plus O2, Cu2S plus O2 giving Cu2O plus SO2. Copper oxide is obtained. The copper oxide again reacts with the copper sulfide to obtain pure copper metal. This is then subjected for refining. Next, extracting the metals in the middle of the activity series. As the name suggests, these metals are moderately reactive. They are present as sulfides or carbonates ores. The first process is to convert these sulfides or carbonates into oxides. Sulfides ores are converted by heating strongly in excess air. This method is called roasting. Carbonate ores are heated in limited air. This process is called calcination. As you can see the example, zinc sulfide is done roasting and zinc oxide is formed. Zinc carbonate is calcinated and zinc oxide is formed. The metal is thus obtained by reducing the zinc oxide. Zinc oxide plus carbon is giving zinc plus carbon monoxide, CO. The zinc metal is done for refining. Next, extracting metals towards top of the activity series, which means this is an extraction technique used for very reactive metals. The metals here are very reactive. These are mainly obtained by electrolytic reduction. A sample image is shown here. Metals like sodium, magnesium, calcium are obtained by electrolysis of their molten chlorides. Metals are deposited at cathode and chlorine is liberated at anode. As you can see in the picture, this is an electrolysis of NaCl, molten sodium chloride. When this happens, sodium metal is deposited at the cathode and chlorine gas is liberated at anode. Refining of metals. We discussed how to extract metals from their ores, but the extracted metals are not completely pure. These impurities are removed by refining. The most widely used refining method is electrolytic refining. As you can see here, this is a simple setup image of electrolytic refining. In this process, the impure metal is made the anode and a thin strip of pure metal is made the cathode. A solution of the metal salt is used as electrolyte. On passing the current, pure metal from anode dissolves in the electrolyte. An equivalent amount of pure metal from the electrolyte is deposited in the cathode. The soluble impurities goes into the solution. The insoluble impurities settle down as anode mud. This is the broad procedure happening here. Let's look with an example here. In the picture, you can see copper. In this setup, we have taken the impure copper metal which is extracted as the anode, and a thin strip of pure copper is taken as cathode. Copper sulfate solution is taken as the electrolyte. As the current passes, as the process starts, what happens here is the pure metal part from the anode, which means the impurity is kept in the anode, the pure copper comes from the anode and it is flows into the solution. To make everything neutral, to maintain equality, an equivalent amount of copper passes to the cathode, which means the thin strip of cathode becomes larger and the anode size decreases. Also, the insoluble impurities settle down below the anode as anode mud, and the soluble impurities in the extracted form dissolves in the copper sulfate solution. So this is what happens in the refining. Next, how corrosion can be prevented. You can see three different test tubes here. Here we have nails dipped in test tube. In the first case, there is free air and water present, which is the water is here and the nails are dipped inside. In the second case, the nail is dipped in water and we have a small column of oil filled and the air is above that. In the next case, we don't have water, but instead we have a drying agent like the compound here, calcium chloride, which means the air is captured by calcium chloride to keep the test tube air free. So, if we just keep these test tubes for some time, we can observe the changes in test tube A. We can see rusting is happening in test tube A. So, no change occurs in B or C. Why? This is because moisture and air are the two main reasons or the two main primary sources that comes as a result of corrosion. Moisture and air acts on the metal surface and corrosion occurs. In B and C, either air is not present or moisture is not present. So, corrosion is not there. This is what takes place with corrosion. So, how this corrosion can be prevented? There are several methods to prevent corrosion. Galvanization is a method of protecting steel and iron from rusting by coating them with a thin layer of zinc. Next is rusting of iron can be prevented by painting, greasing, oiling, etc. One of the important techniques to prevent corrosion is alloying. It improves the properties of the metal too. For example, pure iron is soft and it stretches easily when hot. When mixed with small amount of carbon, it becomes hard and strong. Iron mixed with nickel and chromium gives stainless steel, which is hard and doesn't rust. If one of the metal in an alloy is mercury, it is called amalgam, which have wide range of properties. The electrical conductivity and melting point is lower for alloys. As you can see, brass and bronze. Brass is an alloy of copper and zinc. Bronze is an alloy of copper and tin. Both are poor conductors of electricity. Solder, as you can see here, is an alloy of lead and tin. It has low melting point and it is used in welding of electrical wires. So, an alloy is something which is a homogeneous mixture of two or more metals. This can easily prevent corrosion.